Okay, this is, where are we? Lecture 9, part 2, or one of the 3 parts, formal charge. You are being introduced to formal charge to learn to use it, but you're actually not going to apply it in detail until next semester. But this way, when you reach it, you will have had some experience with it. So I highly recommend you just go through the steps. You learn to go through the steps, and it's bookkeeping. And so if you just follow the bookkeeping steps, don't make 2 of the common mistakes I made in an earlier lecture, because I went too fast. So why do we care about formal charge, and what is it? Formal charge is bookkeeping. It's accounting and chemistry, and it's related to the flow of electrons, similar to polarity, how you have an unequal distribution. It's kind of like that, except it's bookkeeping. It's just a way we keep track of electron distribution. We're looking for the lowest energy Lewis structure of a molecule. Sometimes you can have more than one Lewis structure for the identical molecule. Now, we're not talking about isomers this time. We're talking about, you know what the molecule is, you know what's connected to what, but the way the bonds are laid out can be different. So we use the formal charge system to identify the lowest energy form. You're going to use this in Chem 1 when you use resonance. And resonance is something, if you see this structure, this is resonance. This is a representation of the 3 forms that make up the actual, in this case, nitrate ion. We don't have a way with Lewis structure to actually draw what we find in the lab. So formal charges are used to kind of get the best fit structures. So like I said, learn to apply the rules this semester. Don't worry too much about why you're going to apply them next semester. But I just want to show you, this is what's called a resonance structure. Each of these oxygens is actually unique. You can call it O1, O2, O3. They look the same, but they're not. It's just a chemistry thing. When we go into the lab and we measure the bond lengths in a nitrate ion, this bond has a specific length. A double bond is shorter than a single bond. We know what those lengths are usually. You can look them up in tables. When we go in and we look at the nitrate bond, each NO bond is slightly longer than a double bond and slightly shorter than a single bond. But we don't have a way to represent that with Lewis structure. So we draw a resonance, which is each contribution to the whole structure. Now these pretty much the same, but see, it has to do with redistributing the bonds. It's not, you're not rearranging anything. It's all about the number of bonds on each. Sometimes though, the possible structures you can have are going to look different. These all look the same. It's an N connected to an O. It's just a question of where's the double bond. The real structure is a hybrid of these. Okay, that's just an introduction. You're not actually going to apply it this semester. You will next semester. So when we're looking for either which is the lowest energy, sometimes we have contributions. If these were 3 slightly different structures, they were all contributed to the actual structure. The actual structure had components of each. Like I said, the NO bond is a hybrid of a double and a single. We say that a certain structure gives a certain weight. Maybe one of the structures is the best, and so we say it's 70% contribution. Another one's 20%, another one's 10. How do we know which is the best structure? We calculate and assign a formal charge. So the formal charge is assigned on each individual atom, all right? And you put the number next to the atom. So I'm going to show you how we do it, and then I'm going to show you how we decide the lowest energy structure. That's this set of rules. And then I'll work through a couple examples. So I'm going to go to the whiteboard. All right. So the example, I'm going to use nitrate just to show you how to assign a formal charge. And so you have to assign formal charge off of a Lewis structure. We're not doing this on Vesper, we're doing it on Lewis structure. Now, because this is a nitrate ion, you have to put the Lewis structure in a bracket with the charge. Don't forget that with ions, even polyatomics. Now, when you calculate formal charge, don't do the mistake I did earlier and get them backwards. It doesn't work. What's the first thing you do? You're doing this for each atom. What is the valence electron number? The second, what are the actual electron count around the atom? You subtract them. 1 minus 2 equals your formal charge. That's all there is to do it for assigning it. Just don't get them backwards because it won't come out right. All right. So let's start with this oxygen. We're going to call this oxygen 1. This is identical to this, so we can call them both oxygen 1. So oxygen 1, the valence number for oxygen is 6. That's an O1. Subtract the number of electrons that are actually on it. So each pair you count as, each individual dot is an electron, and a bond is 1 electron. So the bond counts for 1 in a formal charge. So it's 1, 2, 3, 4, 5, 6, 7. So you have a -1 formal charge here, and you put it right next to the atom. And remember, very important, formal charge is for individual atoms in a structure to determine the best lowest energy structure. This is identical to this, so this is also -1. I'm going to put my numbers in a different color because that's confusing. So that's oxygen number 1. All right, here's oxygen number 2. Oxygen number 2. Again, we have 6 valence electrons. You get that from the group number on the periodic table. How many electrons are around this? 1, 2, 3, 4, 5, 6. 1 for each bond. So that's 0. Okay? What about the nitrogen? Valence electron, or nitrogen has 5 valence electrons. Bonds count as 1. 1, 2, 3, 4. So that's a +1. You put the signs with the formal charge. Now we're going to look at the rules. First of all, the sum of your formal charges has got to equal the sum of your ion. If it's a molecule with no charge, then the sum has to be 0 because a molecule has no charge. But if it's an ion, the sum has to equal the ion's charge. So +1 and -1 will cancel out, so you have a -1. So that matches. You cannot break structural rules when you're looking for a best fit. So I might give you an example and the numbers are beautiful and you want to say, yep, that's the best structure because of the numbers. But if I broke a structural rule, then no, that will not be the correct answer. So pay attention to structural rules to see if any of them have been broken in your structure. The other thing, 2 other things. One is, and this isn't the list, your neighboring charges have to be of opposite signs. I can't have a +1 next to a +1. They have to be opposite. Remember, repulsion and attraction. Okay? And then the other, and I'll give you another example that demonstrates this. Oh, this kind of does. Any negative charges are best on the more electronegative atom. In this case, the negatives are on the oxygen, which is more electronegative, and so that's fine. But if you have a choice and everything else is the same except for where the negative is, it wants to be on the more electronegative atom. That's lowest energy. All right, so this is how you do it. Again, it's bookkeeping. Step, just to assign it, the formal charge, just go through and assign the numbers. Don't overthink it. Valence electron number from the periodic table minus the actual count. Count the electrons. A bond counts as 1 because, you know, we're only looking at the actual electrons that are contributed here. And this is only for, even though this is an ion, these are covalent bonds, and so it's covalent bonds. All right, so it's just the valence minus the actual. That's your formal charge. So if you can assign formal charges and then tell me which is the best structure based on the rules of formal charge, you're in good shape. So I'm going to do another example, and this is going to use, I'm looking. So there's a slide, a clicker slide, and it says, what's the formal charge of carbon A ion? So let's go ahead and do that in case you're looking at the slide. You'll have the answer. And again, don't break structural rules. When I did this in a lecture, I put the wrong number of dots because I was going too fast, and it didn't come out. Because it won't. You have to do it right. Remember, details. Okay. Let's make sure I do it correctly this time. So this is carbonate ion. What's the carbon? Carbon has 4 valence electrons, 1, 2, 3, 4 bonds. So that's 4. Carbon is quite often 0 because it quite often has 4 bonds. Okay. Let's do these guys. We'll call these oxygen. Oxygen 1. And this will be oxygen 2. Don't get that confused with the formal charge. My blue is just my numbering. So to keep track of it. So O1, valence number for oxygen is 6 minus 1, 2, 3, 4, 5, 6, 7. So it has a formal charge of -1. This is identical, so it also has a -1. Oxygen 2, this guy down here, valence number 6 minus 1, 2, 3, 4, 5, 6, 0. Okay. So these are my numbers. Double check. I just didn't break any structural rules, and my negatives add up. My charges add up to this. Remember, that's just my numbering system in blue. Look at the green. So a -1 formal charge plus a -1 gives you me a -2. So yes, they add up. The sum of the formal charges equals the whole. Okay, I want to do an example now where I show you how we can use it to determine the lowest energy structure. So I have this ion, and you're told to find the lowest energy structure out of 2. So first you have to draw the 2 Lewis structures. And before you can do that, you have to count your valence electrons. I have 4 for carbon. I have 6 for oxygen. I have 5 for nitrogen. Don't forget the ion. I have 1 for the ion. Do not forget your negative charge. 10. I wrote a nitrogen instead of 5. 5. 15, 16. Carbon is the least electronegative. You're going to put it in the middle. Remember that for designing Lewis structures, the least electronegative goes in the middle. So put a nitrogen on one side, oxygen on the other. 2, 3, 4. Remember, it's an ion, bracket it, put your charge, double check my valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, and everything has got an octet. That's one of your possible structures. This is another one, perfectly acceptable. Again, carbon is in the middle, but nitrogen can have 3 bonds. It often does. And oxygen will have 1. Oxygen, you're not going to generally see with 3. Remember the oxygen Lewis structure dot structure? It usually will have 2 bonds. It's not going to have 3. I can't think of any example. Okay. Number of valence electrons, 2, 4, 6, 8, 10, 12, 14, 16. And my negative charge. So how do I know which one of these is the lowest energy structure? Which one is probably more likely to be what you're going to find? That is where formal charge comes in. So we go up here and we say the carbon, it's 4 minus 4, 1, 2, 3, 4, 4 bonds equals 0. Like I said, carbon is usually 0. This carbon, valence number is 4, 1, 2, 3, 4, 0. Okay, very common. All right, oxygen. This oxygen, valence number is 6. Can you see this? Hang on, I think I've got my, I don't know if that sits in the way or not. Valence number is 6 for oxygen. We have 2, 4, 5, 6. So that's 0, okay? The nitrogen here, valence number of 5, 2, 4, 5, 6, minus 1, okay? My sum equals my charge. My ion is a minus 1. I have a sum of my formal charges is minus 1, so that's fine. Let's go down here, oxygen. Valence number is 6 minus 2, 4, 6, 7, minus 1. Nitrogen, valence number of 5 is 5 minus 2, 3, 4, 5. So that's 0. And once again, the sum of my formal charges equals my ion charge. So what's the better structure? Go back to that electronegativity rule. Your numbers are the same, 0, 0, minus 1. There's nothing next to each other that would conflict, no negatives next to each other. So we have a -1 on nitrogen, and over here we have a -1 on oxygen, which is more electronegative. If you look at your periodic table, oxygen is here, nitrogen is here. Oxygen is further to the right, it is more electronegative. Therefore, the lowest energy structure is the one with the negative formal charge on the more electronegative atom. And so it's this one. This is actually the preferred structure. It's the lowest energy, and this is how we determined it, by using formal charge. So it's bookkeeping to assign the lower energy structure. Okay, one more. And that's phosphoric acid. Here's my notes. H3PO4. Now, I want to use this to point out something that I told one class and forgot to tell another. When you do Lewis structure, there are 3 exceptions to the octet rule. For this class, there are more. In Chem 1, though, you're going to learn why. And so you'll be able to figure out the others. But for here, just know you are going to see 3 or be expected to be able to use 3. Boron can have fewer than 8 electrons. So boron can have 6 bonds and be perfectly happy. So 6 electrons is okay for boron. All right, that's an exception. You only have 3. This is the only one that's less than. So boron can have less than 8 electrons, and that's fine. So if you're doing a Lewis structure and you have boron and you can only get it to work with 3 bonds around boron, go for it. You're good. Phosphorus and sulfur can have more than 8 electrons. Okay, you're going to learn why in Chem 1, but just know right now, if you can only get something to fill the, draw a Lewis structure with the correct number of valence electrons distributed by putting 5 bonds on phosphorus or 6 bonds on sulfur, you can do that. Or if you're given one of these examples, it's okay. So memorize these. Boron can have fewer than 8, this is for your octet rule, and phosphorus and sulfur can have greater than. It can have more than 4 bonds. It can have more than 8 electrons. All right, and I'm going to show you one of these examples. So first we do the Lewis structure for H3PO4. And I already know, all right, I shouldn't shortcut. So this is 3 valence, right? 3 times 1, 3 valence electrons. Phosphorus is 5. And oxygen is 6. And you have 4 of them. So that's 24, 29, 32. So I have 32 valence electrons to distribute. Phosphorus is here. It's less electronegative than oxygen. Most things are. So it's going to be my center atom. I'm going to put an oxygen around each side. I'm putting the hydrogens on the oxygens because I know that's where they go. Okay, let's put our dots. And count them up. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 32 valence electrons. Now I'm going to calculate the formal charge of this. Oxygen, so notice, so the oxygens on this side, valence number is 6, 2, 4, 5, 6. So these 3 have formal charge of 0. This oxygen, valence number 6, 2, 4, 6, 7. Right? So it has a -1 formal charge. That's a -1. Here, let me write this next to it. Okay, so it's a -1 formal charge. My phosphorus has a valence number of 5. It's underneath nitrogen, -1, 2, 3, 4. Okay, so I have a -1 on this oxygen, a formal charge, a +1, but my net charge as a molecule is 0, and sure enough, these will add up to 0. Okay, but can we do another conformation that is a lower energy? And I didn't leave myself much room. Okay. So this is with single bonds all the way around. Let's go up here. And there's my phosphorus, oxygen, 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 hydrogen. These guys are going to be the same. Right, because you don't have much choice. You have these hydrogens, they have to go on the oxygens. There's really no place else to put them. So you can't do anything with these. So, but this oxygen, I can take one of these pairs and share it with the phosphorus, and that's what I'm going to do. So this pair, I'm going to share both of the electrons with the phosphorus and make a double bond. I still have 32 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, I have another structure that fits all the rules. Yes, I have 5 bonds on phosphorus, but phosphorus is one of your exceptions. You're allowed to do that, which is really convenient. Now let's do formal charge. These oxygens are still going to be 0. We haven't changed them, okay? This oxygen, valence number of 6 minus 2, 4, 5, 6. It's now 0. The phosphorus, valence number is 5, 1, 2, 3, 4, 5. It's now 0. This structure has no formal charges. Everything is evenly distributed because this reflects an uneven distribution of electrons. This is a lower energy level structure than this one. And sure enough, if you go to the internet, it would help if I share it. All right, one guy. And we look for the structure of phosphoric acid. Look at that. That's what you find. You will find this structure with the double bond because it's the lower energy. And how did we know it's the lower energy? From Lewis charges, or formal charge. So that's the purpose of formal charge. Don't overcomplicate it. Take every single where are we here? You do it atom by atom, all right? You're not doing for the whole molecule, you're doing for the individual atom. Just do the math. Valence electrons minus the actual electrons there. If it's unshared pairs, you count them individually. If it's a bond counts as 1. Each bond. Subtract them. Valence minus actual, that number is your formal charge. Write it down. When you're done, make sure you haven't broken any rules. Again, we didn't break the octet rule for phosphorus because that's an exception. We're allowed to do that. Now check these. Make sure you follow these guidelines. You put the negative charge on the most electronegative atom. You have any charges that are next to each other are opposite charges, right? And then you select the structure that has the lowest set of formal charges. It has the lowest numbers. I went from a -1 and a +1 to a 0, 0. So that's it. That's formal charge. How you're going to apply it, you're going to use in Chem 1. This is just learning to work through it. Don't overcomplicate it. Just follow the steps and you'll be fine. And that's, at the moment, all there is on formal charge. So, until next time.